Hello? Hello? Can you hear me? Can you hear me? Well, if you can hear me, then you probably already know a little bit about sound. You experience sounds every single day. It's one of our five senses. You start learning about those senses in grade one, as I've come to understand from my daughter's class, and and we use it sometimes even when we don't realize it that we're using it. We use it to locate things. So when we hear a sound, we can be able to turn towards that sound, even though um, the sound waves are going off in all directions. So you have an idea of what a sound is based on the way that you perceive those sounds. In this chapter, we're going to be looking at uh, how we detect sound later. We're going to be looking at the loudness or volume of sound, and surprisingly, there's a lot of times where you're hearing things and you don't even realizing that you're hearing them. The hum of the air going through ventilation shafts, the vibrations in the walls, the rattling in lights. And so we hear sound sometimes even when we don't realize that we're detecting them. So we're going to look at how loud sounds are and the mathematical system of determining that. But first, we're going to look at what a sound wave actually is. So sound is a form of, like pretty much everything that we talk about in physics, it is a form of energy. If you think about what we've done so far, we looked at motion, which is basically kinetic energy. We looked at forces, which is a way of changing energies. We had an entire unit on energy, gravitational, kinetic. We did some thermal stuff. We talked about other types of energy as well. Everything that we do in physics is talking about energy in some form, and sound is no different. So it's an energy resulting from oscillations in pressure of the medium in which the sound is traveling. So we looked at longitudinal waves earlier, and we talked about longitudinal wave being a result of changes in pressure. And when that changes in pressure is something that can reach your ear, we call it sound. So as we just discussed, sound is a longitudinal wave. Since the particles vibrate, and you should be able to remember this, the difference between a longitudinal and a transverse wave is in a longitudinal wave, the particles vibrate parallel to the motion of the wave, creating areas of alternating high and low pressure. So the particles group together, as we saw in the last chapter, where the particles group together, we get a high pressure, and where the particles are more spread apart, we get a low pressure. And that high and low pressure will move through the medium, and that's what causes the motion of the sound wave. Areas of high pressure are called compressions. Not surprising, you're compressing the particles into a smaller space, and that's what creates the high pressure. The areas of low pressure are word that you probably haven't heard before, although it might sound kind of familiar because it sounds like something else you've heard. The areas of low pressure are called rarefactions. Kind of sounds a little bit like refraction. Totally different thing, although they do both have something to do with waves. This is a rarefaction. So we look over here. I've got a website you can take a look at if you wanted to get a little bit more detail. Here's the idea of our compressions and rarefactions in sound waves. So on the top diagram, we have a tuning fork, which is vibrating. When the tuning fork pushes out, let's see, we're looking at the particles to the right of the tuning fork. So when the part of the tuning fork on the right pushes to the right, it compresses the air next to it, which compresses the air next to that, which compresses the air next to that. When the particles move over to the left, it's stretching out the air and creating a rarefaction. So we can see how that compression seems to move along to the right. On the bottom diagram, it shows you if we were to just take a picture of the top diagram at one particular moment in time, you would see that you would have an area in here and in there where the particles are all compressed together. There's your compression, and then obviously in between them we have areas of rarefaction as well. Between the rarefaction and compression, you get your equilibrium point. Somewhere in the middle, your particles will be exactly where they would normally be if there was no disturbance. And the closer you get to the compression, the more the particles are moved away from their equilibrium point in one direction. The closer you get to the rarefaction, the more that the particles have moved away from their equilibrium point in the other direction. So when we're talking about the idea of wavelengths in a longitudinal wave, the wavelength is this distance here from compression to compression, or from rarefaction to rarefaction. That is the wavelength in the air. So let's go back to our note. We don't hear all sounds. We are able to hear some sounds, and there's two characteristics about the wave that will determine whether we can hear it or not. You've probably heard if the idea that if a tree falls in the forest, does it make a sound? It's supposed to be a philosophical debate about whether humans being able to detect something is what causes it to come into existence. How do we know that a tree makes a sound if we're not there to be able to detect it? Well, that's where science comes in. Science should not be based on whether we are there or not there. If sound is a vibration of the particles in a medium, then those particles should continue to vibrate regardless of whether there's somebody there to detect it or not. So we can hear some sounds depending on, well, first of all, its volume. Volume is how loud something is, and if it's not loud enough for you to hear, then you don't hear it. Doesn't mean that it's not producing a sound, it just means that you don't hear that sound. And the other thing is the frequency. So there are certain frequencies that humans are able to hear, somewhere in the neighborhood of 20 hertz to 20,000 hertz. Different creatures can obviously hear at different frequencies, which is why a dog whistle will work well for a dog, but humans won't be able to hear it because they can detect frequencies that are above that 20,000 hertz. As you age or as you have hearing damage, that range of frequencies will change. So instead of being able to hear, say, 20 to 20,000 hertz, you may find that sounds at 18 or 19,000 hertz you can't really detect anymore. There are apps. I know I have an app for my iPhone to be able to test that. It's actually a pretty simple app. It by no means would take the place of an audiologist if you think that you do actually have hearing problems, but it's a neat little free app that you can use to test your hearing. So we talk about volume in terms of the actual wave. We know what the frequency is in terms of the wave. It's how often those compressions are happening, how many times a second. The volume is based on the amplitude of the wave. So the higher the amplitude basically means that the particles are going to be compressed more. So the compressions are more extreme. You're squeezing the particles in the medium into a much smaller space. By putting it to a smaller space, there's more compression, which is a higher amplitude, which sounds like a louder sound. Frequencies, as we just talked about, frequencies that are in the human hearing range, that 20 to 20,000 hertz, are said to be audible. Audible means something that you can hear. I suppose that this is a relative term. Maybe for me, a 19,500 hertz might not be audible to me. Maybe 22 hertz isn't audible either, but you, being younger, would be able to hear that sound where I might not. You probably think years back, before when cell phones were very, very strongly discouraged in classrooms, And if you were caught using a cell phone in classroom, you were probably down in the office and getting your cell phone confiscated. People would try to devise ways of being able to receive messages without their teacher knowing. So they would have these really high pitched ringtones. The idea with a high pitched ringtone is that your teacher, being probably older and with some hearing loss that inevitably happens through life, might not be able to detect that 19,500 hertz hearing or sound. And that could work, and it would definitely work with some people, but not everybody. And it's not necessarily your younger teachers are going to be the only ones that were able to hear it. I was able to hear those. I can still hear those frequencies. Hopefully, I will continue to be able to hear those frequencies. But odds are that as I age as well, that those are going to be gone. So frequencies above this range, we have a word for that. And it has to do with sonic being things that you can hear. Above the range are ultrasonic. So you've probably all heard of ultrasound. So the idea with an ultrasound is sending a sound wave at a frequency that's too high for people to hear, sending that sound wave into human tissue. It will bounce off just like a fish finder would work. The sound wave bounces off materials that it can't go through, and then when it comes back, it can be detected by a device which will produce an image. Frequencies below this are called infrasonic. One of the ways to think about this is think about a visible light. Think about different types of light rays that you would have learned in grade 10. There's ultraviolet. Ultra means more than. It means above violet. And then there was infrared, which means less than red. So in this case, the ultra and the infra go along with sonic. Ultrasonic means higher frequency, and infrasonic means lower frequency. Well, we know that the way that sound waves move, because they're longitudinal waves, is that they're based on the density of the material. In areas with high density, that's where your compression is. Areas of low density represent your rarefactions, and it's the movement of these high density and low density regions that dictate how the sound wave will move. So the waves move based on the density of the particles. So it would make sense that as there are some materials which will allow their particles to move around more easily and form areas of high and low density more easily than others. So you would expect then that the speed that the wave travels will depend on the media, the material in which it's traveling. So here I have a list of a few different materials. I'm going to talk about the speeds. All our speeds are going to be measured in meters per second. Air will have a speed of somewhere in the neighborhood of about, on a really, really cold day, you might be looking at, say, 320 meters per second. I'm talking really, really cold here. And on hotter days, you might be able to get up to extremely hot days, you might be able to get up to in the high 350s. Let's say even to 360 meters per second. So somewhere in that mid 300s type of range. Water, on the other hand, has a speed somewhere in the 1400 to 1500 meter per second range. So you can see it's way, way faster, and that might be counterintuitive. You would think that sound would be able to travel faster in air. Well, you think of how the particles will be able to move, and think of a longitudinal wave as a jostling of particles. Now, if I were to take our physics class of, let's say, 20 people into the gym, and and I provide some sort of disturbance to people on one side, and give them a little bit of a push, in order for them to form a compression someplace, it's going to take them a while to bump into somebody else in order to form a higher density area. And then once they do that, that person is going to take a while to bump into another person in there. So since the particles are all spread out, it takes a while for the areas of high density to be able to move through the gymnasium. If I were to look at water, that might be, instead of taking just the 20 people in my class, maybe I can take like 200 people that I taught this year and put them in the gym. And now when I push somebody, so the particles are more densely packed. When I push somebody in one end, they're going to bump into somebody next to them, which is going to bump into somebody next to them, and it's going to be able to move a lot easier. So what about if we're looking at ice then? Ice has a speed of about 3,200 meters per second. So why does it move faster than the ice? Well, remember that in a solid, the particles are essentially very closely attached to each other. So this would be, again, like if I were to take people in the classroom, head out to the hallway and have you each join arms and try to keep your arms rigid. And when I push one person, because they're completely joined with the person next to them, pushing one person will result in pushing the person next to them. And so the wave will move down the line much easier than if the people were just kind of wandering aimlessly around the hall like they would in a liquid or in a gas. So along with this idea, the speed of sound in steel tends to be about 5,000 meters per second. Glass tends to be somewhere around 4,000 meters per second. Granite is closer to 6,000 meters per second. And just when you're thinking to yourself, well, this is easy, as solids, the particles can move faster, and you're going to get really high speeds in solids and medium speeds in liquids and low speeds in gases. And then we take a look at rubber, and the speed of sound through rubber is somewhere between 40 and 150 meters per second. When we think of how rubber, the characteristics that rubber has, we can imagine that the particles have a lot of elasticity, so they're not as rigid. So imagine this to be more like the same example I was giving you before. Everybody lines up in the hallway. You link arms, except you leave your arms very, very loose. So when I push one person on one end, because the two people's arms are loose and they can bend, they might not really push the person next to them. They might not end up pushing the person next to them at all. Or if they do, it's a very, very slow process, which is why the speed of sound in rubber is considerably less than the speed of sound in any of these other materials. So you'll notice in quite a few of these, and even the ones where I didn't put them in, there's a range. So air, 320 to 360. Water, 1400 to 1500. Rubber, 40 to 150. That last one with rubber is probably based on the type of rubber you have. But even ice and steel and glass, there is a range of speeds, and we can't say specifically what the speed is because we need a little bit more information. There's something else that's going to affect the speed of sound in these materials, and that something else is temperature. I suppose that pressure, external pressure might have a little bit to do with it as well, but temperature is the big thing. So for most media, there's going to be sometimes a considerable difference. Like if you look at air, going between 320 and 360, we're looking at a 10% difference there, a little over 10% difference. A little under 10% for water from 1400 to 1500. And so the difference is based on the temperature. The higher the temperature, the more spread out the particles are. And you would think that would result in air, you would think that would result in a lower speed because of how spread out the particles are, but it turns out that the natural speed that the particles have mean that they move around more quickly, and you actually get a higher dependence. We can look at this experimentally in a particular media. The easiest one to look at is air. And so if we were to just determine the speed of sound in air for a whole bunch of different temperatures, we can then graph that. And so on this on this graph here, we have temperature as our independent variable because we're going to change the temperature. We have the speed in meters per second. We'll say this temperature is in degrees Celsius. And now we can go and try to graph this. And what you actually get is something that looks a little bit like that. So it's a straight line, and of course, as soon as you see a straight line, you think, hey, I should probably get the equation for that straight line. So one of the things that we're going to want to know is what that intercept is. That intercept occurs right at t equals 0 degrees Celsius, and it turns out to be about 332 meters per second. The slope of this line is equal to very close to 0.59. Sometimes you might see it as 0.6, 0.59 meters per second per degree Celsius. So when we combine all of this, using the idea of having an equation, y equals mx plus b, well, it's not y in this case, it's v. It's the m value is 0.59. It's not x, it's p. And the intercept, as you can see, is 332 meters per second. So this equation is an equation that tells us what the speed of sound is in air, depending on the temperature of the air. We could use this, we can notice that the speed of sound gets lower and lower in air, and you would think that you might be able to use this to determine what absolute zero is, but the problem is that once you get to a certain temperature, the air will actually condense, turning into a liquid, and very, very quickly freeze and turn into a solid, in which case the graph would change. So it doesn't continue. We saw with water and ice that there was a considerable different temperature. So water at 0 degrees Celsius is going to have a speed of about 1400. Ice at 0 degrees Celsius is going to have a speed of about 3200. So there's a big discontinuous nature to the graph that you would get. So we can't continue this line forever. It will get to the point where the air condenses and the graph basically stops. But for all reasonable values of air temperature, we don't really need to talk about what's going to happen to air when it condenses or freezes. We'll just look at reasonable temperatures anywhere from, say, minus 20 to maybe air temperatures inside furnaces or stoves that could end up in the hundreds of degrees Celsius. This graph will work. So let's use it in an example. It's a fairly simple example on the next page here. Determine the wavelength in air at 10 degrees Celsius of a 440 hertz sound. 440 hertz is a relatively low frequency sound. To give you an idea of frequencies, and I'll show you a little bit more of this in class, a 1000 hertz frequency is the tone that you would get, like a standard tone that you get on, say, like an emergency broadcast, or the standard tone that you produce when you just want to make a one frequency sound is usually 1000 hertz sound. So what does this look like? Is a diagram all that useful here? Probably not. I'm a big fan of drawing diagrams when they're appropriate. In this case, it's probably not appropriate. So what do we know? We know the temperature of the air is 10 degrees Celsius. We know the frequency of the sound is 440 hertz. We need to get the wavelength, and in order to get the wavelength, it means you need the speed of sound. So V is equal to 332 plus 0.59 t. I've rearranged the equation a little bit. That's just the way I learned it, but it doesn't really matter which term you have coming first. So 332 plus 0.59 times 10, which gives you 332 plus 5.9, or 337.9 meters per second. good idea here that because we have three significant digits. This is an addition. We have three significant digits in the 33.2. Our lowest value here is in the ones place with the 2. So you might be tempted to chop off that 9 because we don't have a decimal place in that first number. So if you're going to follow, strictly speaking, the significant digit rules, you might want to chop off that decimal. I'm going to recommend that you don't. We could very easily just add another decimal place in there. But a lot of our calculations will be very dependent on that last decimal. So it's a good idea to keep at least one more decimal place until, at the very least, until your final answer. You know the wave equation, V is equal to F times lambda. Lambda then is equal to V over F, which is 337.9 meters per second divided by 440 hertz, which gives us 337.9 divided by 440 gives us about 0.768 meters, or 76.8 centimeters. So when you hear a 440 hertz sound, it's roughly an A. If I remember correctly, it's an A. If you're playing A key on a piano, kind of in the middle of the keyboard, you would hear that 440 hertz sound. The compressions that are being produced in the air are going to be almost 77 centimeters apart. So it has a fairly long wavelength, especially when you compare it to some of the wavelengths you would have been looking at with light last year, where the wavelengths would have been in nanometers. So the reason the wavelengths are so much larger in sound is basically because the frequency is way, way smaller. That the sound waves are being produced at a much lower frequency than light waves. So a couple of questions that I want you to consider. First, that's not what I wanted to do. Add a page in here. So, question number 1. Does a 1 hertz vibration produce a sound? So wave your hand in front of your face. Wave it so it goes back and forth every second. So it takes half a second to go in front of you, half a second to go back. You can look at a watch, you can time it, you can go every second. That is a vibration. It is vibrating the air around you. Is that producing sound? So think about that. We'll talk about it tomorrow. The second thing that I want you to do is to devise an experiment to determine speed of sound in air. We're going to want to go and do this. So let's say that we have the ability to go outside. I'm not going to try to do this in classroom. It would be too difficult. But let's say we can go outside and measure the air temperature outside. We're going to have some very rudimentary equipment. I'm going to give you access to measuring tape. I'm going to give you access to stopwatches, if you don't have them already, and some sort of quick noise-making device, like just clapping your hands or something that will make a very quick sound. That's all you need in order to get a reasonable value for the speed of sound. When we look back a couple of slides ago at the graph that we would get down here, we have to figure out how it is that we would get each of these speeds. Now, we can't control the air temperature outside, but I suppose if we wanted to, we could do this over a series of a few days, measure the temperature in each one of those days and come up with our own graph and see if we can reproduce the results that they have here. That might actually be possible. I've never tried that before. That might be an interesting thing to do now that we have time in class to be able to do these. So I want you to come up with your own method of how this is going to work, and we'll see if we can come up with something that works and perform this lab as a class.